All right, welcome to this topic 7.4. I've kind of redone a few things. So this is a new video lesson and is out of sync of prior recorded videos. In this video, I'm going to work through the process of how we predict products of a synthesis reaction versus a decomposition reaction. Synthesis reactions, as we learned from our classifying component of the unit, is one in which an element combines with an element to produce a compound, where A and X in this situation can represent two different elements forming a compound. Again, there's lots of different scenarios of where a synthesis reaction can take place. We're going to stay in the mindset that they are going to be ionic, meaning a positive and negative. But I just want you to understand that if you go on and experience chemistry elsewhere, that there is more to this than what we're going to dive into at this point. Okay? One of the things that's going to be very critical for this unit as we continue forward and this lesson is this acronym that I use here. Not every chemistry teacher uses this acronym. This is one that was passed along to me and is stuck with me, and I think it sticks well with you guys. I pronounce this Hoffenkleiber, and Hoffenkleiber is a way of, again, identifying elements that are what we call diatomic. Diatomic means that hydrogen, for example, doesn't exist as H, but it exists as H2. Oxygen, like we did in our combustion reactions, is O2. We have F2, I2, N2, Cl2, and Br2. So all 7 of these exist in nature on their own, again in a diatomic state. So what we're going to work on first is coming up with our product, like we did with the combustion problems. The thing here is it doesn't have a predictable outcome like a combustion problem, and we have some steps to do. So in order to determine what these two make, we don't just simply add them together, but we have to figure out what they make based on charges. You're going to need your periodic table with your charges, okay? And so if you recall from chemical naming, we know that positives go first in an ionic compound and the negatives go second. So calcium is here with a +2, sulfur is here with a -2. So what I have is calcium, when it combines with sulfur, because their charges individually is a +2 with a -2, I'm going to see that these charges cancel as I cross them down. So the outcome here is going to be CaS, and it looks like I simply just added them together, when in fact I didn't. It took one of these to cancel one of these, and the thing that's great is this works out to be a balanced equation. We see this 2 show up. Again, oxygen is one of those 7, okay? So that's why oxygen has that 2, but the calcium, sulfur, and magnesium do not, is because magnesium, magnesium, calcium, sulfur, these 3 are not one of those 7 diatomics. Oxygen is. When we go to come up with the formula, that 2 sticks with oxygen when it's in the diatomic state. Subscripts are going to come from charges, so we need to look up the charges for each of these. Magnesium is going to make a +2 charge, oxygen is going to make a -2. So what I'm going to see here is magnesium with a +2 charge combining with oxygen of a -2. What happens to the charges here is that as we cross, they're going to cancel. So that 2 that was present on the oxygen over here was there because oxygen was diatomic. In this case, it's now bonded to magnesium. It needs one of these to knock out one of these, which is why it's a 1-to-1 charge. Remember, we can go and add coefficients to then show balancing. This is 2 oxygen on the reactant side, so I'm going to place a 2 here on the product side. Remember that this 2 changes the oxygen, but also the magnesium. I'm now going to place a 2 on the reactant side, and I'm now balanced. The last one has copper. When you look at your periodic table, if you recall, this is the D block, transition metals. They vary in charge, which is why I can't look at my periodic table and say, oh, but copper is this charge. It doesn't have and work that way. So this is why I have to give you this copper +3 here on the end. Like example A and B, copper is going to have a +3 charge. It's combined with nitrogen. Okay, so of all of the 6 examples of elements here, oxygen and nitrogen are diatomics, which is why they again have those 2's there as an element. Here, when copper is going to combine with this nitrogen, nitrogen makes a -3 anion. So what I see happening, and I really must have liked this when I came up with examples for these notes, is that again, the running theme here is that charges are going to cancel out. I would then use a coefficient 2 to balance those nitrogen, which then would require 2 in front of the copper. Decomposition, as we learned on reaction types, is just the inverse. So we're going to break things up. So we have something like AX is going to split up into elements A and X. It's building blocks. Because again, the only thing we could do here was combine the elements together. Down here we have a compound. The only thing we can do is break it up. So here the splitting point is, I have sodium and I have chlorine. So my products, A is the sodium, X is the chlorine. The thing you have to be careful when predicting products of a decomposition situation is you got to look out for those Hoffenklebers again. Sodium is not one of the 7. Chlorine is. Chlorine gets a subscript 2. Sodium will not. We have 2 chlorine on the reactant side, so I'm going to put a 2 on the product side, excuse me. So I need a 2 on the reactant side to take care of the chlorine. That then changes my sodium to 2, and a 2 is needed there, and now I am balanced on my reaction. Again, for B, we have an ionic compound. The only option is for this to decompose into the elements that make it up. Aluminum plus oxygen. The only subscripts I could decide to carry forward are those that are from the diatomics. Aluminum is not, so it's going to stay a 1. Oxygen is going to need a 2 because it's Hoffenkleiber. Again, over here, when I look at the reactant side, these 2s and 3s are here because of charges and what was crossed down. Coefficients are added to balance. I can start by balancing my aluminum, but what I find is I now have 3 oxygen on the reactant side, 2 on the product side. So ultimately, that's going to be undone. There's nothing I can take times 2 to get to 3, so these both go into 6. So to achieve that, I'm going to place a 2 on the reactant side. That gives me 6 oxygen. To place that 6 oxygen on the product side, I know a coefficient 3 is going to be needed. Again, this 2 applies to both elements in the compound. So 2 times my subscript 2, that gives me 4 aluminum. My subscript here is 1, so my coefficient of 4 is what's going to be needed here. For C, again, all we can do is decompose. So we break them up. Silver and nitrogen. Silver is not Hoffenkleiber, so it will not receive a subscript. Nitrogen is Hoffenkleiber. It gets a subscript too. Like example B, we could start by balancing the silver, but we're going to find it gets undone quickly because there are 2 nitrogens on the product side. So to get 2 nitrogen on the reactant side, I give that a 2. That coefficient then changes and balances the nitrogen. Silver are now a total of 6 on the reactant side. 6 is going to go on the product side, and we're balanced. Okay. So when they're mixed together, you have to decide, is it synthesis or decomposition? I see that I have 2 reactants, and they're both elements. The only thing I can do is combine them together, so this is synthesis. They combine together through charges. Beryllium is a +2. Oxygen is a -2. So we have Be +2, O -2. Do not do this work in the formula, because otherwise you're going to have a lot of information and you're going to end up getting a little lost along the way. So with crossing of charges, they cancel, we get BeO. I can see I have 2 oxygens on the reactant side, so a 2 is needed on the product side. That means a 2 is needed on the reactant side for the beryllium, and we're balanced. B and C are the same reaction type. I only have 1 reactant, and that reactant is a compound. The only thing we can do is decompose it. B is going to break apart into silver and oxygen. C is going to break apart into strontium and nitrogen. When you look at these and you go through decomposition, you have to find your diatomics. Silver is not. Oxygen is, so it gets a 2. Strontium is not one of the 7. Nitrogen is, so it gets a 2. For both of these, you then balance. There's a 2 in the silver here, so I could put a 2 here. Oxygen, there's 2 on the product side. There's only 1 on the reactant side. So I'm going to place a 2 on the reactant side. That changes my silver to 4. So I need to erase that coefficient. This is really 1 silver. So in order to make that true, I need to place a 4 here to really give 4 silvers. Nitrogens I can see are balanced, strontium or not. Coefficient of 3 on the product side, and that takes care of balancing. So this was a quick run through on how to predict products when you are looking at a synthesis versus a decomposition reaction.